Okay, yeah. Can you guys see my screen? Okay. Um, I'm not using an earpiece, so kindly forgive me for that. Okay. So let's start. Okay. So for today's lab, we are literally going to walk through linear regression, right? But instead of us using um, the linear regression model, which is coming from the Python library that we have been using, we are going to go through the normal algebraic method in order to this one. I don't know. Sometimes it messes up the sound. Let me see. Hello, Richard Star Bismarck. Please, am I audible? Oh, okay, sure. So I'll start from here. Okay, but can you also see my screen, or I should zoom in a bit? Please, is my screen visible? Okay, sure. All right. So we are going to build the linear regression model, right, using the matrix we or the matrix method, right? So instead of us using a pre-built library that we have to use to train the model, we are going to use the normal equation which we were taught in class, right, on Sunday the last time. So it's basically a one standard linear equation that we have broken it down in the matrix form to get this normal equation here that we have. The b is equal to a transpose of x multiplying itself, and then inverse of this term, and then it also multiplies the transverse of x and then y, right? So it is basically, if you take it into the linear algebra form, is the y is equal to b0 plus b1 x1 plus b2 x2. That's right. So depending on the number of features that you get, and then um, the number of the coefficients also increase. But then you have to make sure or take note that every time we have this one constant, which is the b0, which will always be there. Right? Then if you have two, three, four features, then the number of the coefficient b also what increases. Right? Okay. So for the data sets, we are going to use the California housing data sets. So this is a standard data set that is used for you know doing some machine learning testing and like learning in general. So it is we have some features for housing in the California. So the target is the price of the house, right? So we have the target is the price of the house, and then for the features we have eight features, right? We have the house age, the median the median income of the population, right? And then other features, right? But we are not going to take all the features. We are going to take some of the features, and then couple that with the targets, we are going to find the b, the value of the b's, right, which will help us to get the whole equation. I'm talking about the linear algebra equation. The y is equal to b0 plus b1 y1 plus b2 y2, which is then broken down to this. But we are going to use this method because we have to use the matrix method. We're going to use this method to find all the values of b so that we can fix it in the final equation, right? So this step that we take through is the same thing that happens when we are using the standard library, right? And then we are training the model, and we are using a linear regression, right? So apart from that, we are going to find the mean square error, which is the difference between the predicted value and the actual value squared, and then the RMSE is the root of the mean squared error. Then you are going to also look for um, R R square R square, and then yeah, R square. Okay. So we've talked about the independent variables already. So we have two features. We have median income. Oh, let me check. I hope there's no question as of now. Okay. Derek, you are welcome. Okay. So I said the data set, we are using the California housing data set. For our independent variable, which are the x, the x's, right? We have two of them. We have the median income and the house age, and then the dependent variable, which is the target in this case. We have the house value or the house price, right? So we are going to go through the standard way of how we train data, right? So this has been already pre-processed, so we are not going to spend a lot of time cleaning the values, right? So here we are going to load the data. So we have our data here. Then we have two set of features. We have the median income, and then we have the house age, right? So here we just create our variable, right? And then we fetch our data using the fetch California housing function, right? So with this, we have access to certain methods. So apparently this is a whole module itself that contains the data sets, right? And then within the data sets, we can access the methods such as feature names. We can access all the features. We can also access all the targets, right? Which in here the feature names are two. We have the median income and the house age, and then for the targets we have the the house price, which is, or the house value. Yeah. So um, we start to load and then also prepare the data so that we can train it, right? Okay. So this is where we begin more serious work. So here we are going to section them into a way that we can compute using the matrix formula, which is this formula. I hope we are all familiar with this formula, right? So for our x, for our x data, we are going to pick the two features, right? Or we are going to pick the two features from the eight initial features that were available, right? That we have the median income and the house age, right? So if you actually check, let me zoom in a bit. If you check the list, please give me some few minutes. How do you make that? Okay, so it will take. Okay, so is running. Okay, yeah. So I forgot to mention we picked the module right from the sklearn, right, data sets. So this is where we picked it, and then we are using pandas, we are using the matplotlib, we are also using the scikit-learn metrics, which is where we'll be getting our mean square error and the root mean square error, and also r square from there, right? No questions. Okay, so yes, so I want to run there. Okay, yeah. So if you check the list, we have the median income, the house age, which is median income, house age. We have average rooms, we have the average bedrooms, we have the population, we have the average occupation of the people over there. We have the latitude and we have the longitude, right? So we are going to pick the first two features, right? So um, if you actually check the size of the data set, it's over 200,000 lines, right? Like 200,000 lines, and then it's having the eight features, so it's over 200,000 entries, right? So here we want our x's, right, and then our x's are the median income and the house age, right? So we are going to use the method of slicing, right? The method of like a multi-slicing, so that we can do it as a simple way, whilst we are trying to keep it in the matrix form over here, right? So here we use the method called data, right, which is from the Fetch California house in this module, right? So we have this data which gives access to all the data sets. So if you want access to the data sets, you use the California.data to get access to all the over 200,000 lines, and then the eight features, or over 200,000 entries, right? So here is the row, and then here is the column, right? So we are using the slicing method, right? So we say California.data, and then um, the the colon, right, without any start and finish, right? So this means that we are going to access all the rows, right, or all the lines or all the entries for the California data set, right? And then here we are going to access a slicing of 0 and 2. So this from the fundamentals of Python, we know that is going to return 0 and 1, right? So if you check the 0, the first index is the is the median income. The first one, the first index, oh, the second index, which is 1, is the house age. So that's what we are picking. So you are picking all the rows, and then you are picking all the you are picking both. This is the median income and the house age, right? Okay, that's fine. Okay, then we are picking our y vector, which is the feature, right? Which is the feature. So here there's something tricky that we avoid, right? Or we have to ensure once we are doing machine learning project, because it uses a lot of vectors and then matrices, right? So we have to avoid lists as possible, right? Okay. So here, right? So you could see here, we have the targets. So this gives you access to the data sets um, without the target. I mean, that's the actual data, right? And then the California.target gives you access to the whole line of targets, right? But then the catch over here is that in accessing the targets from here, it is a flat list, it's just like lists the like list of numbers, like a very long list of numbers, right? But then because we are going to use the matrix form, we have to convert it into a 2D vector, right? So what we do is that we are going to reshape it, and then the for the reshape is part of NumPy, right? That we use. Let's say you have a long list of data, and then you want to reshape it into let's say 2 by 4, a 3 by 3. Then you can do it in that way, right? So we have the reshape, and then we have these two arguments, right? The first one being -1 simply means that it should take into consideration um the all the length, I mean the the total length of the list, right? So here it is like we use the -1 many a times when we don't know the actual number of the entries, right? But then we still want to convert it to a 2D vector, right? So it's saying that take take the list as it is, right? You are not going to divide it into two. We are not going to make it like 2 by 4. We are not going to make it 3 by something. We are not going to make it 4 by something. That is why we use -1. It's a I mean it's a rule that if you use like -1, you are just like we are just trying to say that take the length as it is, right? Take the length as it is, and then um, we are giving it an extra dimension, which is 1 here, right? So here it is going to convert from a flat list into a 2D vector, right? into a 2D vector. So if you say the 2D vector here, it is actually having rows and column, right? It's having rows and column. So then if you take the the each of the rows is having just one entry. Each of the rows is having one entry. So that is why we've been able to convert the flat list, which if you actually like had a chance to print the whole data, you just see them as a list, right? But here we are converting it into a 2D vector, right? Okay. So here, if you have chance, you can go and learn more about the reshape. Let's say you have like, I don't want to go into much detail. Let's say like you have 12 elements right here, right? Like 12, flat list elements. You can reshape it into 2 6, right? Here you know that they are 12, right? So if you are getting it into 2 6, then it is going to have two sorry I want to say 6 2 here. So it's going to have 6 rows and 2 columns right here, right? So that is why here we are using the -1. We're just saying that like whatever the length of the list is, just take it, right? Instead of you having to say 6 or to specify a number of rows, we are just trying to say that any how the number of lists, um, the or the length of the list, like, we just take it like that, right? And then we should create just one column here, right? So it become a 2D. That's why we have the column and the row. So now it's not a flat list again, but then it's a 2D vector, right? So if we were to make this one -1, right? And then so here is, and then let's say this is like a 20, right? But then like we don't want to do the the calculation ourselves. We could just say like -1 4, right? So the reshape is going to do the calculation itself. So you're going to say that we have 20 elements, right? And then we are creating 4 columns. So if we are creating 4 columns, then it means that we have to share 5 along all the 4 columns in order to get the whole 20 elements. Right? So that's why we are. So then here we get 5, right? So then if you do that, then you get all the 20 elements. So that's how we use the negative one and the 4. So you can go and learn more about it. So here we've been able to get the features, and then we're also able to get the targets in their respective vectors or matrices, right? So if you yeah yeah, so you can see the features. So we have the median. So let me zoom. So we have the median income 8.52. We have the 41 here, house age, and then yeah. Now you can see that here. So this is in a matrix form. That's why we don't have any comma over here. And then we have converted this into a 2D. Right. So this is a complete matrix on this one. Complete matrix. Right. So this is for the targets. One more. Yeah, so that's what happened when we used the negative one. When we did the negative one, right? So now we can see our data. Yes. So now we are going to process this and then like reconstruct it with in this form here, right? So here, this is the famous equation that we all know: y equal to b0 b1 x1 b2 x2. Yes. So and then we have the constant term b0, which is here, right? So um we want to get them in a form of matrix, that famous kind of like matrix that we know, like if we are trying to find the uh, let's say x values. So you have ax equals b. I'm talking about like matrices. You have the value of a as a matrix, but you don't know x, and then you have value of b, then you are going to find the values of x. So that is something similar when it comes to here, but we are going to find the b instead of the x. We have our x values here, we have our y values here from here, right? So we need the b value so that we can get the full equation, right? And now any data that we have, we can predict the y value. Any x data that we have, we can predict the y value. So that's basically what we are trying to do. So in order to convert them into the matrix form, now you could see that we have the matrix here. This is the x1. These are all the x1s, right? And these are the x2s, right? These are the x2s. So we have our x1, then we have our x2. But we don't have any representation for the b0, right? So what are we going to do? It means that we have to add a bias. If we add in a bias term or a bias, it simply means that we are introducing one in front of our features here, right? So that in case we are to multiply with any value here, right, we are always going to get the one, because let's say if there's any value, let, um uh, how do I even explain this? Coming. Okay, so um because we are trying to get the constant term here, right, we have to introduce one. to it, so that like they are all one, right? They are all one, like they are not having any significant representation, because we need it. We need those three data, right, in order to get the b0, the b1, and b2, right? So we will, I mean, it will start to make sense as we go deeper into it. So if we want to get the value of b, we have to add a column of 1 to our feature matrix. So this is the feature matrix that we have, right? That's why we are going to add 1 to it. So we create a ones column, right? Then we are going to add it to um, the x original, right? We are going to add it to the x original. So now we have our NumPy. We are accessing once. So once means that we are going to create um, a data that is um, I mean only one, right? Only one, right? And then we are taking the length of the x original, which is the feature matrix here, right? We are taking the shape, so it should print the same number of entries in the feature set, right? And then it should have it should also be in a 2D, right? So that is that I mean that's it over here, right? So we are going to print this number of rows, right? We are going to print the number of rows over here, right? Because the shape is going to give the number of rows and number of columns. And then we are accessing the first one, which is the number of rows. So that's why we are going to print this number of rows, which has to be the same as the number of rows in the feature set. So this is the feature set here, right? Then we are accessing the shape. Okay. So now, so now we are going to stack it with our feature sets, right? Then now we get our x matrix. So we've started this. We started this, right? We started this, right? So we are now getting our x as a matrix, right? So where is it? So here we use h stack, right? Horizontal stack, horizontal stack. So here we have our ones column, which is ones over here, and then we have the feature sets that was originally here, right? So you can see we have 1, then we have 8.4. I mean the second one, was which was the median income, and the third one was the house age, right? Third one was the house age. So now we have our three columns, and then we have oh sorry, the value was like over 20,000, not 200,000. Forgive me for that. So we have almost, well, we have like 20,740 rows. Then we have three columns, right? Okay. Now we are not going to do a lot of work, right? Because these are all functions method that we have them available in NumPy. So we just have to follow the same step as we are going to solve this. So this is the simplified matrix form of the y equals to b0 plus b1 x1 plus b2 x2, right? That's what we've broken down over here. So what we are going to do first is to get our transpose, which is xt, because we have our transpose to multiply with the feature matrix, then we have the transpose to multiply with the target. Here we have a matrix because we have our 2D matrix, right? So we are going to use the dot t to get our transpose, right? Okay. Okay, so now we have our uh, transpose matrix. So you can see that at first it was what 20,643, right? And then when we transpose it, now we have 3, 20, 640. Alright, 20,640, right? So we know the transpose already. I'm not going to go over. That's like you are taking the all the horizontal, right, entries. Now they are becoming vertical. Like all of them are becoming vertical. So the data that we had here, right, here now is becoming 1, 8 something something, and then the 41, and then we have it all along, right? So now we will be having only 3 rows and then 20,640, columns, right? Okay. So here we are going to calculate our x transpose times x, right? So in this place we want a simplified squared matrix representation of the whole of the target, sorry, the feature matrix, right? So we need a square matrix so that we can find the inverse, right? We need our square matrix so that we can find the inverse. So we have the results here. We are going to multiply our x transpose times x, right? So here we have matrix multiplication, then we have x matrix, then we have the transpose, and then we have the x matrix, and you multiply, then you get your 9 elements, or 3 by 3, this one for here, right? So I wanted to get as let me see, okay. So well, I mean, more or less, these nine these 9 elements here gives a summary representation of all this data here, right? 30,000, so 3 by 20, no question, okay, 3 by 20,640, right? So here it is not anything strange that was done. It is the I mean, each of the this one each of the row values, right, were multiplied with sorry, each of the column values, right, from the transpose were multiplied with the row values of the original matrix that we had here, right, to give all these representation, right? So if you take the non-diagonal values, these actually stand for when I say non-diagonal values, these are diagonal values, the 260, these ones and these ones are diagonal values, right? So if you take these ones, right, they are actually showing you how much two features contributes, right? How much two features contributes in the whole feature matrix, right? So if we could track it well, you see that we had our let me see, we had our median income, and then we had our house age, and then we had the bias over here, right? So if you actually check here, if you check here, right, the last part here is what the house age, right? This is the house age, and then this is the median income, right? So this value that we have here, this value 222985, it's the sum of the multiplication is the sum, right? Is the sum of the okay, so we multiply each of the components from the median income, and the house age, right? And then we added all of them, right, to get this value, right? So we are trying to weigh their contribution that these two features bring into the feature space, right? When you take this one too, when you take okay, this one, the last one is just like a square of the house, the house age. So all components of the house age in the um, um, this one, the transpose matrix, were multiplied with the um, the house age of the original matrix, right? So that's why we had this, right? So if you take another non-diagonal value like this, right? If you take this, right? This is giving the relationship. Okay, it's the same. It's the same over here. Um, okay, which one? Which one? So this. Let me see this one. Okay, this one is the bias one. This two this. Okay, yeah. So that's just by the way. So then if you see the diagonal one, it's just the the multiplication of, oh no, their own values, or the square of their own value. That's why we get, like how much are they themselves contributing in the whole feature space. How much is this contributing in the whole feature space? How much is this also contributing in the whole feature space, right? Okay, so that is by the way. So if you have this simple representation of the whole 3 by 20,000 entry data that we had, it means that we can just simplify our calculation, right? So that's what we are trying to achieve with this equation, right? So now that you see, initially we were not having a square matrix, right? It was what we had, the original x, matrix was having over 20,640 rows by 3, right? It wasn't a square matrix, right? We need a square matrix to find our inverse, right? So then we had to get our square matrix by multiplying the the transpose by the matrix itself in order to get a square matrix, which is a simplified representation of the feature space. Now we come here to calculate the inverse, right? Where we are using a try and except over here, right? We are trying to find the the what's the inverse, right? The inverse of the squared um, matrix, right? So this one is just trying to catch it. So in case it is not a square matrix, then we catch it over here and said it's now the one that we learned, a singular matrix, especially if it's having its determinant to be zero. You cannot have a determinant to be zero, then you cannot be inverted, right? So you're just trying to catch, like, if the matrix is having a determinant of zero, then it will catch the error and say the matrix is singular, and then you cannot find an inverse, right? But that's what we are trying to get. So we find the inverse of the matrix. So this square matrix that we had, we found the inverse and we got this value, right? So this is the inverse that we got. So now we have our xtx inverse already, right? So we have this already done, and then we are going to find xty. So we are calculating xty, So we you use the same method, matrix multiplication of the transpose of x and y vector. So what are we also trying to do here, right? We are trying to like project the the feature space onto our targets, right? Here we are also trying to find their I mean relationship, right? So um, how can the y vector scale each of the features over here, right? So that's why we are trying to multiply them over here. So we multiply matrix multiply. So here normally they are called covariants, right? Covariant. So we are trying to determine their relationship that they bring to themselves, right? So now we find the xty, right? So now we have the xtx, xt, sorry, we have the xtx, yeah, inverse, and we have the xty. So we are going to multiply. So now we have this and we have that. So we are going to multiply, right? So now if we multiply, we are going to get um, three values over here, right? So we are going to get three values over here because this one, the first one, we are going to get we are going to get 3 by 3, right? We get we get 3 by 3 here in the first one, and the second one to you have this x inverse, right? Also um, multiplying here. So here too you get a squared matrix, right? So now if you do the matrix multiplication, right, it will just combine all of them, multiply their individual components, and then you have one value, right? So now to become 3 1, right? So it become 3 1. So that's why we have the first one, the second one, the third one. So this one was possible because of the bias that we introduced, the one that we introduced, right? Because at first we didn't have any representation for it. We had to bring in the bias, right, in order to find our b0 or our constant b, right? So now we have the constant b, we have the b1, and then we have the b2, right? So we have been able to do the linear regression manually, right? So this is what happens. Um, I mean, how the linear algebra algorithm was built. Of course, it is more robust than this, but this is the kind of fundamentals behind it when it comes to algebra and vectors for them. So then we have our values b0, b1, b2. Then we can actually use to form the final equation, which is the y is equal to b0 plus b1x plus b2x, right? So here we have our intercept, it's called our bias. We have the weight, the median income, then we have the weights for the house age, that's b2. So now uh well I didn't run most of them. So we have our intercept to be negative 0.1019. We have the weight of the median income and the weight of the house age. So you can see the weight of the median income is very large than the house age. Right? So this will be like a more important feature when it comes to determining the uh, the house value for the California houses. So this is the final equation that we have. You have the this one, you have the 0.43 and the income. So what's the income, and then what is the house age? Now we are going to verify the solution, right? So even if it was the this one, the linear regression model, right, that we use directly from circuits, right, it is still, like a black this one, a black box, kind of thing, right? So we have NumPy is having a linear algebra, right? LST SQ, right? Which uses optimized solving to get the b values directly, right? So this one uses the direct equation, right? And then solves everything to get the b0, b1, b2, right? So for it is just concerned about the b values, right? Without going through the the matrix way of finding the b values, right? So if we use this method and then we get the values, then it means that um, the actual value that we get and the linear, I mean the matrix or the linear regression way of finding the b values is close, right? Yeah. So here we have our result verification. This is the optimized solver. We have our x matrix, then we have our y vector, right? So um, I mean, that's what I was saying. So the results verification or the linear algebra returns, I think three elements. The first one are the b values. The second one is the rank, the rank of the values, and then the third one is another element that I've actually I've actually forgotten, right? So um this one, um because you're trying to, because we just want the b values, you are just going to get only the first element, and then the r con none two is just trying to say that we should ignore the warning about the the singular matrix, right? So even if it warns us that the the vector is this one singular, we should just like skip that, right? So we have our, we find the result verification, and then we find this all close of the b that we found, the b that we use the matrix to find, and then this optimized way of solving, right? Then you check, is it close? So this one gets the difference between these two values. So if it's less than 0.000, I mean 7 zeros and 1, I mean 0.0000001, then it means that they are actually, you know like very close. So do they match? And then you say that it is true, right? So we have the NumPy built-in way, which is the LST SQ, and then the matrix way, which is what basically happens when you try to use a linear regression model, right? Okay. So now we are going. This is how we have to um, uh, visualize, right? But we have a 2D plane, right? We cannot visualize the one with the bias, right? So and then also with the house value itself, right? So we can try and then make one constant, and then try and find the house value, like how much one feature is contributing, right, to the house pricing or the house value, right? So you can see here, we pick, so we say x original, the feature matrix. We are going to use all the row numbers, and then we are going to use the income, right? So we are going to use the income. Then we're going to plot it with uh, mass processing. So all these blue points are the houses, right? They just represent the houses, right? And this is the house value, and then this is the income, right? Okay. So here to we are now coming to, now we have our values. We are going to generate the line of best fit. So that is what the linear algebra tries to do. So after it finds the v values, then it tries to draw the line of best fit, right? So that we can use. I mean, this is basically the equation, the y equation, right? So um, here we are saying that our x value, we had, like a lot, um like a lot of them. So we are going to create 100, I mean 100 of them, right? So what we are going to do is, you see the x value, the row numbers, they were a lot, right? Like they're a lot, right? So we are going to create 100 equally spaced elements, or equally spaced value, right? And then we are going to find their y values, and then use them to create the line, because I mean, like there is no need to use all the values here, right, to draw it. You can just use we take the minimum value, right? The minimum value here, we take the maximum value here, and then you're going to select 100 equally spaced elements from here. So that's why we are using the length space from. So it takes the matrix, um, uh, the feature matrix, and then gets 100 equally spaced value. And then our mean age, we are going to find the mean. We are going to find the mean because we are going to use that mean, right, to calculate all the y values, right? So we get our this one, the age, the mean age, right? We need it. So we want that one to become constant, right? Just, like what is the average house age that is among the California houses, right? So we have that here, so that will be here. Then we have our x1 rate, which is, we are going to find it like 100 times. So we are going to have 100 y points, right? Then we have our b values already. We have our b0, b1, b2, right? So then when we plot it, we will get this uh, model average, right? So this is what the model drew, and then this is what the actual data looks like. So this is what linear a yeah sorry this is what linear regression tries to do. This is the whole point of linear regression. Then we are going through the algebraic way, right? Okay. So now, to end it, we are just going to test the model. We're going to test the model. We have a sample example here. Let me check. No one has asked the question. So I'm going to test the the model, right? So take notes that the values that you see, they are in the unit of 10,000, right? They are in the unit of 10,000. So I mean, any value that we get for y, you have to multiply by 10,000 so that we can get the actual money value, right? Okay. So we have our example here. The student income is 5, which is 50,000, and then the student's age is uh, what, 20, right? Student, I mean, house age, right, is 20, and then the income is this. So we are going to um, do calculate the prediction. Right now we have our b values, we have the student income, we have the student age over here. So um, it's going to print the prediction for the income and then use the student income and the age, right, to get the predicted value. So here we have 5 and then 20, right? And then the model score gives 2.4054. So you multiply it by you know the value, like the 10,000. So I think it's 100. No, it's 100,000 instead. I think it's 100,000. It's not 10,000. So then you are going to multiply the value. Then you're going to get 240,000. So the last part, the last part is the error. These are the metrics when it comes to the model. How wrong was the model, and then how are the predicted how far are the predicted values from the the actual values. So we have now now we are taking our model, right? We are going to calculate all the y values for it. So then we have our feature space here, our feature matrix, and then we have the b value. And we're going to get all the y's. Right? Now we get all the y's. Now we get um MSE, which is the mean squared error, which is directly we take each predicted value, which is here. This is the predicted value, and this is the real targets, right? The real target and the predicted targets. So you find the difference and then you square it for all the y's, right? So we've done it, and then finding the roots is the root mean square. So that's why we find the root mean square. So this the the value here you get a value. So it basically becomes like a plus or minus something. So if that is the error, right, which your which occurred with your model, right? Okay. So um, if it's low, it means that your model has a higher chance of predicting the accurate value. It is very if it's closer to one, your model has a bad chance of predicting an actual value. So and then uh the R2 is um uh, how much of the feature space did it actually got to do an actual prediction on, or how much of the feature space did it actually got to work with, right? So here is a very very good metric that tells you um, is your model dealing with a lot of noise? Because let's say you get let's say 0.4 or like 40%, right? So it means that your model was actually was able to take 40% of the feature space and then work with it, and then go to do the prediction on it. So the rest of the 60% are a whole lot of noise, right? So then it affects the model performance in the real world, right? So that it got a few of the data sets to actually do real work on it, right? So that is basically what um, the 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 R squared talks about, right? So we have the residual, which sums all the difference between the target value and the predicted value, right? And then the total, also sums the target value minus the mean of the target value, right? And then squares all of them and then find the out. So you could see that the R squared score here is 50.9%. Right? So on average or in total, it was able to take like quite a little bit more than 50% to actually work with it. So a lot of the data, a lot of the data inside the feature matrix are noise. Right? So this could impact the data performance on real world, right? 26 minutes more. Okay. And then um, the root the root mean squared error is 0.805. Right? So the model is off by 80,000. So like I mean any predicted value that you get, there could be the chance of an error of 80,000. Right? So this is how it impacts the model. So in all, we have basically been able to implement our linear regression from scratch using the the normal equation here. So that is all for today's lab. Uh, Let me see. If you have any question, you can ask me. Then we can close from here. So let me end it.